Hello, everybody. So what we're going to be looking at today is section 3.4 in your book, which is derivatives as rates of change. Now, we already covered basically everything in here that is on your homework in an earlier section, but I didn't have a video for this section, so we're going to put it up here. So let's go ahead and get started. So the key to this section is just recognizing this fact, right? So derivatives are rates of change. And you know that because the definition of the derivative was a limit of an average rate of change, and it became an instantaneous rate of change. So derivatives are rates of change, specifically like f prime of, I'll say t here, it doesn't matter the variable, but f prime of t is the instantaneous rate of change of f with respect to t. Just a comment on the units of a derivative, notes, or just note actually. Note, um, so if f has units, I don't know how to write this, so I'm going to say it has units a, and let's say t has units, I'll change that to an x has units b, then the derivative, let's say f prime of x, which can also be written this way, right? df dx has units a over b, right? So on top you have the f, which has units a, and on the bottom you have x, which has units b. And when you do the derivative, you have the f over the x, so the units are the a over the b. Okay, and that's mostly just from the definition of the derivative, where you have the function on top and the independent variable on bottom, right? Like you had something like this, like f of b minus f of a over b minus a in one of your definitions of the derivative. And so down here, this was in the units of x, and up here, this was in the units of f. So that's why this happens. But it's important that you keep that in mind because it helps you keep track of what your units should be in these rates of change problems. Um, so let's see here. I'm going to skip a little bit of this section. I'm only going to do what I think is on the homework. Um, I think the main thing on the homework is projectile motion, or just motion in general. So we'll do motion in general and then projectile motion. So motion. Um, so let s of t, we usually use s for position, be the position or distance traveled by an object at time t, or from 0 to t. I'm just going to say at time t. Okay. Then the derivative of f, or s, sorry, s prime of t, which also has units ds dt, which we might write v of t, is the rate of change of position, which is velocity. Also called velocity. All right, so we have that position, distance traveled, object, time t. So the units of velocity, they're going to be are a distance on top and a time on the bottom. And the reason for that is because we said up here, right, look, ds dt. So the s is position or distance. So that's going to be measured in distance. The bottom is dt, well, time, right? This time was t. So the top's a distance and the bottom's a time. So distance over time. So like velocities are measured in like miles per hour and so on, right? Okay. Now you can do the same thing. And I should say and, not then. And um, the derivative of velocity, which would be, the derivative of velocity, which could also be written as the derivative of velocity with respect to time, which you could also write it as the second derivative of the position equation, is what we're going to call a of t. And is acceleration as a function of time. Um, and that's also the rate of change of velocity. So the rate of change of velocity is acceleration. The units of acceleration are, well, think about it. The v is velocity, so it has units distance over time. So you have distance on top, time on the bottom, and that's just for the v. And then on the bottom, you have a dt. So that's over time again. When you combine all that, it's distance over time squared when you work out the units on acceleration. So this is just kind of a comment to help you keep track of stuff. So for example, if s of t is feet and t is in seconds, then v of t, which is the derivative of s, is going to have units feet per second. That is not what I was trying to do. Twitch just opened itself. V has units feet per second because of what we said here about feet per second. And acceleration has units, well, right here, distance over time squared. So it would be feet per time squared. Okay, now it's really laggy right now because another app tried to open. So I'm going to try to get out of this window and then I have to open it up the window again. But it takes a second. Oh, oops. I see what I did wrong. Again. Okay, we're good. Okay. So that is how like the units on these things work. Okay. Now, yeah. So a simple problem could be like this, just asking you to use these equations. So, example, they say a model rocket is launched vertically upward from the ground with initial velocity 256 feet per second, right? Which makes sense for a velocity, feet per second. The height after t seconds is given by s of t, right? We're going to be using s usually for position, negative 16t squared plus 256t. So just kind of comment on this as well before we get started. This is acceleration due to gravity. So this is just if units are feet and seconds, this negative 16 is because of gravity. So this is like a normal looking equation because like this is Earth gravity according to that negative 16. So you get used to seeing those numbers there a lot. Okay, so that's what was given. And then what they say is when is the height, I'll call this part A. When is the height? No, there is only part A, so I don't know why I did that. When is the height of the rocket? Uh, 1,024 feet. Okay. So to answer this, what you would have to realize is they're asking for a height of a rocket, and in terms of acceleration, velocity, and position, what is that 1,024 feet, right? So that's the first thing to make sure you understand is what they're asking for. So answer. So a height of 1,024 feet uses the position equation, because that's not a velocity or an acceleration. Is a distance or position. And not obviously velocity or acceleration. And you can tell that from the units, for example. Okay, so we don't need any derivatives here. This problem is not asking us to do any calculus. So if you want the height to be 1,024, so you have s of t is negative 16t squared plus 256t. What you would do is this is the height, right? So you're going to replace that with the 1,024 feet, and then this is your equation that you have to solve. So move everything to one side. I'm just going to solve this now. So let's go everything to the left. Like that. And then this is what you have to solve. Now, let me just grab a calculator. 1 second. So I happen to notice that everything there is divisible by 16. So I'm just going to factor out a 16. So if you just factor out a 16 here, you got t squared minus, and then 256 over 16 is 16. So 16t plus 1,024 over 16 is 64 equals 0. Parentheses. We can probably factor that. So to me, this looks like this factors. You could also use the quadratic equation here, but t minus 16t plus 64 looks like it factors into t minus 8 squared equals 0. And from this, I see, you can divide both sides by 16 to get that. And obviously t is 8 now. And that's going to be seconds. And that tells you that that's the time when the rocket is 1,024 feet. So rocket is 1,024 feet at t equals 8 seconds. And so that's what you type into the computer. Why did that lock up? All right, so that's our first try at this. Um, we did not use any of the um, we didn't use any of the equations for velocity and acceleration, so it just started out real easy. Let's keep going. So here's another question. Example, s of t equals 2t to the fourth minus 8t cubed minus 6t squared plus 7, where t is greater than or equal to 0, um, is the position of a hummingbird moving on a straight line. Okay. S is in yards, and T is in seconds. And the question is the bird speeding up or slowing down at t equals 2 seconds? Okay. So what you'd have to do here is they're giving you the position like before, and then they're asking you a question. But what you need to do is interpret this, and they're asking you, is the bird speeding up or slowing down at t equals seconds? So speeding up or slowing you down, they're asking you, how is the velocity changing? Okay. They are asking how your velocity is changing at t equals 2, right? Now, you might think, oh, so we should find velocity. But look at what we have here for our things we can calculate. If you find velocity, so s prime, which is velocity, is the rate of change of position. So velocity actually tells you how fast your position is changing. Whereas when you take the derivative of velocity, you get acceleration, and acceleration is the rate of change of velocity. So if you want to know how fast, um, if you want to know how fast the speed is changing, you actually want to look at acceleration. Okay. And the sign is going to tell us the answer here, but we need to just get in here and do this. So they're asking how your velocity is changing at t equals 2. Acceleration will tell us that, because acceleration is the rate of change of velocity. All right, so let's start out with our S equation here. Just going to copy it and drag it down. So there's your position, right? Or distance. Let's find our velocity. V of t, which is s prime. So we need to take a derivative. So you take the derivative of this function using, in this case, power rule, power rule, power rule. Should be good at it by now, maybe. No, this is only one section after power rule. Maybe you're not good at it yet. But for power rule, you take the 4 down in front. So take this 4 down in front here. So you'll have 4 times 2, which is 8. You subtract 1 from the exponent on the variable, so you get 3. Then for this one, we're going to do the same thing. You bring the 3 down in front. 3 times 8 is going to be 24. So minus 24t to the 2. Then here, 2 down in front. 2 and 6 is going to be 12. Multiplying. Subtract 1 from the exponent. It becomes 1. And then here, the derivative of 7 is 0. So there's your velocity equation. Yeah, let's do acceleration now. There's something I want to do with velocity as well, but I'm going to do acceleration first. So the acceleration, which is the derivative of velocity, and we take another derivative, so the derivative of the derivative. So again, we're just going to do the power roll again to everything. So here, bring the 3 down in front. 3 times 8 will be 24. Subtract 1 from the power to get 2. Here, bring the 2 down in front. 2 times 24 is going to be 48. 48 e to the 1 power. And then the derivative of negative 12t is going to be negative 12. So there's your acceleration. So I've got position and velocity and acceleration equations here. Now what I want to do is I want to do two things. I want to find the velocity, and then I want to find the acceleration at 2, and then I'm going to interpret it. So I'm going to say find velocity and acceleration at 2. Right? Because they said t equals 2 was the point that we care about. So let's find v of 2. So v of 2 is putting 2 into that equation for v right here. So it's 8, 2 cubed minus 24, 2 squared minus 12 times 2. So you just work that out like a calculator or something. So you got 2 to the 3, which is 8 times 8, which is 64, minus 24 times 4 is negative 32, minus 24. So you get negative 56, I believe. And then the units would be, what would the units be? So you have to look at the units of this. So S is in yards, T is in seconds. So its velocity is negative 56 yards per second. Okay. Now, one of the keys here is making sure we understand this number, what it means to be negative. So when you see a negative velocity here, what this is so the velocity or the speed is negative 56. That means the bird's speed is 56 yards per second, and the negative indicates that it is in the negative direction. Right? Because you have like a number line here, essentially. So you have like position 0. And then, you know, if you move this way, that would be positive velocity would move you that way. And if you move the opposite direction, that would be a negative velocity. And I'm drawing it on a line because they said we were on a line. Okay, so that's your interpretation of positive and negative velocity, is just which direction you're going in. So the bird's going 56 yards per second, which seems super fast, but the bird was actually a hummingbird, I think, in the example. I just didn't write it. So that's what we get from velocity. And the reason I calculated that was because I wanted to know the sign. All right, acceleration of 2. So acceleration is up there. I can see it on the screen. So a of 2 is going to be 24 2 squared minus 48 times 2 minus 12. So you got 24 times 4, it looks like, and then minus 48 times 2, and then minus 12, which is minus 12. And the units on that are going to be in yards per second squared. Okay, so what this means is, so the acceleration of negative 12, the fact that it's negative, indicates that the bird's velocity um, is becoming more negative, right? Because of the negative sign on there. Okay, so the bird's velocity is becoming more negative. So if it's starting, if the bird's velocity is negative, so v of 2 was whatever it was, negative 56 yards per second is already negative, right? Is a negative velocity. And according to what we just did, the a of 2 was negative 12 yards per second squared, is negative, which means that velocity is getting more negative as well. Right? So that means that if the velocity is negative 56 and becomes more negative, then the bird would be speeding up, right? So if v is negative and becoming more negative, then the bird is speeding up, right? So that's why we had to look at the signs on both of these things, because if this was a positive 12, it would become, then the velocity would have been becoming more positive. And if you take a negative 56 and make it more positive, the number would get smaller, which would mean the bird is slowing down, right? So I needed to know the signs on both of these to answer this question. And we did. Okay. So let's do another one here. Blah, blah, blah. Nope, that's too easy. I'm looking for one that got something to the problem. Okay, yeah. Hey, it's a problem that looks just like I wrote it. I always do potatoes. Um, so a potato is launched vertically upward with initial velocity. I don't know why they keep telling us the initial velocity without us doing anything with it, but initial velocity 34 feet per second. I think it's just so you can see it. Atop a building that's 15 feet tall. Right? We're just standing on the roof shooting potatoes up in the air. So the height of the potato at time t, which is in seconds after the launch, is s of t equals negative 16 t squared plus 34t plus 15. So again, we can just comment on this. This is from gravity. This was your initial velocity. And this was your building height. This is like the launch height, basically. So that's where like the numbers come from. You could, I mean, you can derive this equation. You don't have to like know those facts, but for now, we can just, I'm just noting them that that's why the numbers look familiar. Um, and then the question is, how long is the potato in the air? Okay. So the graph of position looks like this. So this is our answer now. Okay. So you have time here and you have height here. So the potato starts out at a height of 15. That's because that's how high the building was. So we're starting from there. At time 0, you're 15 feet off the ground because you're on the roof. Now, then what's going to happen is the potato is going up. So it goes up in the air, and then it's going to come down, and then it's going to hit the ground. Okay. So the two things that they make you find on this graph a lot are how high it goes and how long it's in the air. Um, those are the two things that it makes you find the most. So the most common thing to find is this maximum height. The second most common thing is where does this hit on the t-axis, right? Like this isn't like throwing it horizontally from the building, right? This is time, not like x. So these are the two positions that you often have to find. So this one right here is the max height, which we were not asked for, but the max height. And the way you find this is at the time there, the velocity is 0 because when the potato was going up, velocity was positive, and when the potato is coming down, velocity is negative, and right in the middle, its velocity is 0. So the max height, v equals 0 here, and that's actually how you find it, is you set velocity equal to 0. Now here, where it hits, this is going to be where the potato hits the ground. At that point, the position is 0. So do you see the difference? If you're looking for the maximum height, you have to set velocity equal to 0. But if you're looking for where the object hits the ground, you want s equals 0. And for us, we are being asked how long is the potato in the air, which means basically we need to know when it hits the ground. So that's what we want. We want to know when the potato hits the ground. So knowing what we now know, we set position equal to 0 and solve. All right, so you just grab your position equation. So you grab your position equation. This does not involve velocity at all. Again, another one that doesn't. Set it equal to 0 because that's when it's on the ground. And we have to solve this. Now, these numbers we can't solve by factoring. Whenever, like, I don't think we can, right? So we'll have to use the quadratic equation or a computer. They want an exact answer. So or a computer. I'll do quadratic equation and then we'll use a computer. So, for quadratic equation, right? What is it? It's like normally, I'll write it in general. X, for us it's t, but x negative b plus or minus square root b squared minus 4ac over 2a, right? So for us, we're going to have t equals negative b is negative 34, right? We're looking at a, b, c. So we're looking at negative b plus or minus square root b squared minus 4ac over 2a. So you work that out, grab your calculator, work out the inside of the square root first. I've got 34 squared minus, but it's minus a minus, so it'll be a plus. 4 times 16 times 15, that's 21. Oops, hold on a second. Exit 2116. 46. Awesome. Okay, so we get t equals negative 34 plus or minus square root. I just did this on a calculator over negative 32. So I've got t equals negative 34 plus or minus. That square root actually works out even. 46 over negative 32. And then, so your two solutions are, there are two solutions, are t equals negative 34 minus 46 over minus 32, and negative 34 plus 46 over negative 32. So if you work those out with all the minuses and everything, we've got negative 34 minus 46, which is negative 80 over 32, negative 32, and you get 2.5. You get t equals 2.5 seconds, and t equals, if you do the other one, negative 34 plus 46, which is 12 over 32, which is, as a fraction, 3/8. So this is going to be, what is it? Negative 3/8 seconds. Okay, now I want to look back at this graph here. So when you look at the graph, the reason there's two is because we know from here goes up and comes down, right? This is that 2.5 seconds. Okay. Now what's the other one, the negative 3/8? The negative 3/8 is if this had gone this way, you would have had the negative 3/8 there. But that's not the right answer, right? Like this is definitely the one that you want. That's where it hits. Negative time was before we launched it. So you have to be able to interpret your answer there and say it hits at 2.5 seconds, which means it was in the air for 2.5 seconds. So the potato was in the air for 2.5 seconds after its launch. Okay. So go. Okay, I'm going to do one real quick. I've only got a couple minutes left before I have to stop this and do office hours, but so I'm just going to write it real quick. So a ball is launched upwards. Okay. Its height is s of t equals negative 16t squared plus 256t. And then the question is, what is its velocity when it first hits 880 feet. Okay. And so what's going on here is this. You've got, again, time here, height here, ball, I guess that's S, but starts at 0, goes up, comes down, hits, right? Now, 880 is a height. So somewhere on here is 880 feet. Okay. And if you go over here, there's 2 times where the ball is 880 feet high, right? So there are 2 times that the ball reaches 880 feet. How do you find them? Well, you find them exactly the way we found, the way we did the previous problem. You set the height to 880 and solve the equation. So set S of t equals 880 feet and solve for t to find them. So you have your S of t here. So you just go equals 880, move everything to one side of the equation. You're going to get 0 equals 16t squared minus 256t, it's a t, plus 880. Let me see if 16 goes into 880. It does, 55. So divide everything by 16. I get t squared minus 16t plus 55. I try to factor that, factor or quadratic equation, but I don't think factor will work. So I will use quadratic equation. And I'm not going to write it here because I'm already running out of time. I'm going to tell you what the answer is. So, oh, it does factor. It does factor. Oh, 0 equals t. So like it factors into 11 and 5, right? 5 times 11 is 55. 5 plus 11 is 16. Or negative 11, negative 5 is negative 16. So it does factor. Okay. So the ball is at 880 feet at t equals 5 and t equals 11 seconds. So there's 2 of them. So that's 5 and that's 11. Okay. So 5 seconds is the one we want, right? Why? Because they said specifically they want the first time it reaches that height. Okay. Now, what the actual question is, what is velocity at that time? Right? That was the actual question. So we need to calculate velocity. So you've got to take your position equation here. You're going to compute velocity by taking a derivative, right? S prime negative 32t plus 256, and then plug in 5, right? Plug in t equals 5. That's what we need. And you get v of 5 is negative 32 times 5 plus 256, so 6. So negative 32 times 5 plus 256 is 96. So you get 96. And for units, it's a velocity. We were in feet and seconds again, so velocity is feet per second. So that's the answer to the question. right? So do you see how we had to do multiple things here? We had to deal with the position equation first and then the velocity equation. That's not unusual on these. Um, okay, so that has to be it for now because I need to do my office hours. I hope this helped. I think it will.